Hi, thanks for joining us for Understanding State and Application Workflows with AWS Step Functions. My name is Rob Sutter. I'm a Senior Developer Advocate on the serverless team here at AWS. In this session, you're going to learn a little bit more about the details of step functions and how your workflows actually execute. This is an advanced session for users who are already familiar with step functions, but if you haven't used step functions workflows before, don't worry. I'll give you a quick but brief overview. We're going to touch on some of the Amazon States language improvements that were introduced in 2020. We're going to take you through the life cycle of a single step in a step functions workflow and show you how the input and context data are transformed before, during, and after your task invocation. We're going to talk about handling errors and the built-in retriers and catchers that step functions provides you. You're going to learn three models for parallelism and concurrency, different ways of invoking multiple tasks simultaneously. And finally, I'll leave you with some additional resources for you to continue learning more about step functions workflows. Step functions are essentially business processes. You transition an input through a series of states, and at the end, you have an outcome. If you've ever seen a business process workflow diagram, that's exactly what step functions do for you. And you can use this for building data transformation workflows, IT operations and security remediation workflows, and even serverless applications. So with that brief overview, let's get started with the Amazon States language improvements. Now, as I mentioned, these are new to the Amazon States language, or ASL, and introduced in mid-2020. There were a number of changes made. First, we made updates to the comparison operators in the choice state, and there's a number of these that we'll walk through individually. We provided global access to the context object. I'll give you an example of what this means and how it helps you shorten and clarify your workflows. We provided dynamic timeouts, the ResultSelector, which is a new way of manipulating your data before you return it to the state. We give you a string construction operator, a string to JSON and back converter, and we give you an array construction operator. You'll see at the bottom of the slide there's a link to the blog post where we announced all these changes. I recommend you follow that link and have a quick read through the blog for additional details. It also includes the code that you'll see in the upcoming slides. So the first set of changes we introduced with the improvements to the Amazon States language revolved around the choice operator. We gave you additional comparison operators so that you can make your choice based on more factors. The impact of this to you is that you can make these choices directly in your workflow without invoking an additional Lambda function. And this translates to reduced invocation or workflow runtime and reduced cost for you. The isNull operator that you see on the slide compares a given variable in the state and sees if it's null. The isString, which you see an example of on this slide, checks to determine if that variable is a string. And the same for numeric, Boolean, and timestamps. This allows you to ensure that the data that you expect is in the proper format before you take an additional step. It also lets you use dynamically typed languages to put values back into the state and branch down different workflow paths depending on the type of object you got back. You can also check for existence with the isPresent operator. Now, it's important to note that this is not the same as isNull. This checks to make sure that a key with the value that you specify is actually present in the state. The isNull operator checks that the value of that key is null. So you can use these two in conjunction with one another, but they are not the same operator. Here you see on the slide an example of where we've checked to make sure that the error key is not present. This is a success condition. If it's not present, we move forward. You could also check to see if the error key is present or equal to true, and if it is, you branch down an error handling path. We give you string matches for simple wildcard comparisons on values in the state. A couple things that are important to note here. This is a case-sensitive string comparison. So uppercase hello, or in the example on our slide, simple in all uppercase will not match the condition that we've specified here. However, anything that begins with simple, as written here on the slide with an uppercase S, will match our comparison operator. The wildcard comparison operator, or asterisk, can also be matched against. Now this is a good case if, for example, you're doing security remediation workflows and you want to look for IAM policies that are too broad. The actual key that you'll be looking for is an asterisk. To compare against that, you'll want to escape it with 2 backslashes. So if you're looking for something that matches asterisk, it's backslash, backslash, asterisk. There are no other characters besides the asterisk that have a special meaning during matching. This is not a regular expression pattern matching operator. This is simple wildcarding based on strings that you specify and the asterisk or glob operator. Next up was variable to variable comparisons. You can have 2 operations that each return dynamic results to your state. Previously, if you wanted to compare those two, you needed to invoke a Lambda function. Now you can compare them directly within AWS Step Functions. In this case, we take the value stored in result1 key and we compare it to the value stored in result2 key. If they're equal, this succeeds. If they're different, it returns false. Again, just like with the string match, this is a case-sensitive comparison. So you need to be sure that you're comparing against the exact value that you need. And there's not currently an option to make this a case-insensitive comparison for either. So those are our comparison operators in the choice state that we updated. We also gave you access to the global access to the context object, which means you can access it from anywhere in your workflow. Previously, you could only access it from within certain state types, but now you can access it in the input path and output path, items path when you're iterating through a map state, the variable itself in a choice state, for example, to compare an initial value of your workflow or the start time of your workflow, the result selector, and comparing variables to variables. That is, you can compare a variable in your state, which is separate from your context, to some value in your context. And this should make more sense when we walk through the single step later in this presentation. Now, the power in global access to the context object is in elimination of steps and simplifying your workflows. Previously, if you wanted to compare the information in your state at execution start time to some value, for example, to make sure it was later than a certain time, you needed to do that in 2 steps. The first was the pass step that you see on the slide, which moved the value from the context execution.startTime into the top level of your state. Now with global access to the context object, you can do this inline, and you can make your choice based on whether the execution start time was greater than a time that you specify, as you see on this slide. Dynamic timeouts were a great feature. When you run tasks using the wait for task token, or callback as it's informally known, pattern, then you provide specifications for how long the task is allowed to run and how frequently the task should send back a heartbeat or check in to let you know that it's still running and hasn't errored out. Previously, you needed to specify these as integer values at the time of deployment. Well, that wasn't ideal because you can have changing conditions in your state, or you may even want to prioritize workflows over one another at different times. Now with dynamic timeouts, you can specify a timeout seconds path or heartbeat seconds path, where you would have specified timeout seconds or heartbeat seconds before. And you can set this value programmatically, either with your initial value to the state or as a result of some operation in a previous step. You can specify both of these or one or the other. They can also be used with timeout seconds. You may, for example, want to define your timeout seconds path dynamically but have a heartbeat every 5 seconds as a constant for simplification. The ResultSelector is an extremely powerful new feature that was introduced with the ASL improvements. The ResultSelector allows you to take the raw output generated from a task, parse and filter it, and only select the items that you need for inclusion into your state. Now, this is especially useful when you're doing map or dynamic parallelism and iterating over a large number of fields. Native SDK calls and service integrations, in this case DynamoDB put item, can return a lot of information. In fact, this is 2.8 kilobytes of information that previously you would have returned to the state of your application. With the ResultSelector that we specified on the previous slide, you can turn that into this, only capturing the information that you care about and returning that to the state. In this case, our 2.8 kilobytes of returned text is shrunk to 74 bytes. This is 37 times smaller. This is, again, huge for map state items where you're iterating over a number of parallel processes. The string construction operator, or string templating, is also available now in the Amazon States language. You use a pair of open and close braces for each variable that you want to replace in a template string. And then you add additional arguments, in this case, first and last in the JSON path for your state, to replace those templates. In this way, you would get a string constructed that says, my full name is Rob Sutter, assuming we're using my information in the state. Previously, like many of the other operations, you had to invoke a Lambda function to do string interpolation. Another common use for Lambda functions for maintenance was JSON to string and string to JSON conversion. Well, now you can do this inside your step function workflows as well. This is a very common occurrence when you're using DynamoDB integrations. You probably have a piece of your state that you want to insert as an entire value under a string key in DynamoDB. Well, now as you see on the slide, you can do that in one call. It's also a safe conversion, which means we're taking a common but solved problem and giving you a declarative solution for it. And that's what step functions workflows are all about. Lifting commonly repeated tasks out of your code so that you can focus on your business logic. The final improvement that was made to the Amazon States language is array construction. This is similar to string construction, but for when you have a number of items that you want to consolidate into an array. The example you see here on the slide builds a one-dimensional array from the IPv4 localhost, the IPv6 localhost, and the source IP that we defined in a previous step in our workflow. Now, one thing that's important to note here is there's no flattening in this function. So if our source IP key pointed to a list value, we would now have a two-dimensional array. If you have an array of items that you need to flatten, you'll still need to take that into a Lambda function. However, for most common use cases, this allows you to perform what you need to do. So with those improvements, what does it look like to be a single step in the workflow of a step functions workflow? That is, if you're one task state, how is your data brought to you? How is it changed throughout the process? And how is it put back into the state object for you to move forward in your workflow? Well, it all starts with an event. And this is what you pass to your workflow on invocation as the input. And this gets stored in the root of your state object. So you can think of your state object as looking exactly like this JSON object that you see on the slide at the point in time when your workflow begins to run. Here we have one event from an Amazon EventBridge event bus under invoking event, augmented with some additional data, a table and a cluster ID. This could be an EMR cluster, for example, and a DynamoDB table name, but this is a constructed event that we pass in to start our workflow. Along with the event, You have the context object that we referred to previously. The context object provides metadata about this invocation of the workflow that's running right now. It tells you its unique identifier, when it started, what the original input was to the workflow. It gives you information about the state that you've entered, some similar info such as when it started or when the executor entered that state. How many retries are currently underway for this state so that you can make decisions that way. And it gives you the ID of the state machine and a task token if this step is a wait for task token or callback task state. So we've shortened this for the example, but under execution input, you would have the exact same value that you see on the right. And that's going to persist throughout your entire workflow so that you can compare the value of your state at any given step with what it was originally. So as these two objects feed into your task state, they go through a certain order of operations. The first is the input path, then the task itself, the result selector, the result path, the output path, and finally its return to the state. Now, the input path can also be changed by parameter builders, but because they work in the same way, we've chosen to show you input path here on the slide. So if we take our initial event and we apply input path invoking event, as you see on the header of this slide, we reduce our event down to the fields that you see on the right. We've unnested that invoking event object and moved it up to the root level. Now, in doing this, we also temporarily, inside this step, lose access to table name and cluster ID. But we've done this because we no longer need that information in this step. The state is currently unchanged and will remain so until we get done with this series of operations. Now, in our case, we're considering this a simple money transfer request. Transfers, by their nature, have to be idempotent. So before we attempt to process this transfer, we're going to attempt a conditional DynamoDB put item call to create a lock. That's the task state that we're working through. This call succeeds if no item already exists because that means no other workflow is trying to process it. And it fails if we already have a lock. It means processing is underway. So we don't need the additional information. What we need to create this lock is the information about the transaction itself. And that's why we filtered it down to what you see here. The next thing we do is we take that event on the left and we pass it into our task state. In our case, this is a DynamoDB put item service integration. And as we've seen before, the results of those service integration API calls can be quite extensive. You see what you get back on the right. And it's probably too small for you to read while you're looking at the slides, but don't worry about that. The information itself isn't important. It's the fact that there's too much for you to parse and you don't want to store all of that in your state. So now, this is what we're working with as our state for this step. Again, we talked about the result selector. The result selector that we've shown here at the top is to take the status code, which will be 200 or an error, take the request ID and the request date, which is when the lock was created, and we're going to return those, and that becomes the object that we're dealing with in this step. So now, what you see at the bottom, the 3 lines of status code 200, the unique ID, and the timestamp are what our step is holding in its temporary memory. Now we apply a result path. The result path is part of merging, or is actually merging, that temporary memory with our original state that was brought into the application. As you see on the header for this slide, we've given a result path of detail.lockinfo. Now, detail was already an existing field in our input to this step. So what we're going to do is put the lock info back into detail. It's important to note that this is a destructive merge. So if we had specified items that already existed exactly as they were, we would overwrite them. However, in this case, we are merging those items because there is no namespace collision. If there was information in lock info before, that information would now be lost. But the rest of the information further up the hierarchy in the state remains untouched. So now this is our temporary information held in, our temporary state held in memory for this step, and we move on to the output path. The output path comes after the result path and does something different. The result path is the merge. The output path is what am I going to carry forward into the next step. In this case, all we want is the detail. We've let the rest of that information go, and we're going to keep the detail from the event combined or merged with our lock information and result path, and we're going to move that forward. So now, this is the information that gets stored in our state, and we move forward to our next step for processing, which repeats itself until we reach the end of our workflow. So again, as you look across the bottom of the slide here, you merge your context and input using the input path to form the input that you provide to your task. Your task returns its own information, which you filter with the ResultSelector, and then merge into your existing input with result path. And then again, you filter that merged output using output path to determine what moves on. So that's essentially what happens as you walk through the happy path. But as our CTO Werner Vogel says, everything is failing all the time. Or, put more elegantly, complex systems run in degraded mode. We know that we're going to hit failures. It's a part of building distributed systems. They're complex by their nature. So how do we handle errors in our workflows? Well, for starters, handle them in your workflows. Don't handle them inside your functions. Step Functions gives you two powerful tools for handling errors, and they're solved problems of catching errors and retrying errors as they occur. The first we'll talk about are retriers. Retriers are valid for task, parallel, and map states, and they allow you to attempt to reprocess the entire state in the event of a failure. They're basically switch or case statements on the error equals value. Two values are shown here on this slide, and they match in order. So if you receive a states.timeout order, you are not going to retry at all, as defined on this slide. However, for any other order, you'll retry a maximum of 2 times, waiting initially 3 seconds and backing off by a factor of 1.5. So that means you'll have your first invocation, which was an error. That's attempt 0. You'll wait 3 seconds and have your first retry. If it fails again, you'll wait 4.5 seconds and have your second retry. If that fails, you'll move on. At this point, you've waited for a total of 7.5 seconds. The default for backoff rate is 2, which gives you an exponential backoff that doubles in seconds as you go. Now again, max attempts of 0 is a special value. This means that you won't retry anything for a specific type of error. And that's also the default. Catchers, by comparison, are when you've decided that you want to handle an error rather than retrying the request. They're also known as fallback states. Similarly, they're valid for task, parallel, and map states, and they're scanned in array order, and they're essentially a case or switch statement on those same error types. You get a result path for storing the error once you've processed this type of error, or when you move forward to your next state, so that the processing state or workflow has access to the error values. That's stored using the result path key, as you see in the first catcher on this slide. On this slide, if we receive a timeout error, we'll move forward to our recovery state, which does some operation with the value in error info to attempt recovery. But if we receive any other type of error, we're just going to move on to our end machine state. For parallelism and concurrency, you have 3 choices that are built in, and which one you choose depends on the type of workflow that you have. Parallel invocations are essentially independent. This is provided for you by the concurrency built into Step Functions workflows. An example of this would be if you ran a regular task to look for security groups that were in violation of corporate policies. Each security group that was sent back would be remediated individually because they could be in violation in different ways. And so those are individual workflows that happen in parallel almost by default. The second is dynamic parallelism, and this is the map state. It's when you have a collection of items inside your business process that the workflow itself generates. So whether it's go out and list all orders or list all items in a user's shopping cart, you create a collection of items and then iterate through that collection, applying the same logic to each item. An example would be an order fulfillment system that locks, pulls, and packs each item in a customer's order. And finally, there's function native concurrency. This is outside of Step Functions. This is inside your Lambda function when you're using the primitives of your programming language to perform tasks in parallel or concurrently, depending on the language. This is when the function itself generates the items. For example, if your workflow is clean data in a bucket, the function itself may parse the bucket looking for the items that it needs to clean, and then dispatch a separate thread, routine, go routine, depending on your runtime, to perform the cleaning itself before consolidating all of the results and sending the result back to your workflow for the next step. A bit more about dynamic parallelism, or the map state. In 2020, the size of your state was increased from 64 kilobytes to 256 kilobytes. It's important to know that you can't exceed that when you're dynamically adding items into your state. Your max concurrency during map state is theoretically limitless if you set it to 0, which is the default. However, because of the way that the map state is implemented on a single host using host affinity, the number of concurrent invocations will actually be limited to 40. This means that once you hit 40 concurrent invocations, you will have to wait for one to complete before the next one begins. Now, there's a special value for max concurrency as well. If you have a collection of items but you want to iterate through them one at a time, ensuring that processing is complete before moving on, for example, a banking batch run overnight where you need to complete an entire transaction for each payment before moving forward to the next for balance reasons, then set max concurrency to 1. This doesn't give you the benefits of speed of concurrency, but it does allow you to apply the same task or nested workflow to every item in your collection. So, in review, today we've gone over a few of the Amazon States language improvements introduced in 2020. We've walked through the life cycle of a single step from input and context all the way through when it returns its output back into the state. We've touched a bit on handling errors with retriers and catchers. We've discussed 3 types of parallelism and concurrency, and given you use cases for when to select each and which is most appropriate to certain types of workloads. And now, as promised, some additional resources if you'd like to learn more about step functions. All of the resources that we've referenced in this slide are available at the link you see on the slide here, s12d.com/svs406. There, you'll also find a learning path on step functions, which goes in depth in a series of videos to take you through many more features of step functions workflows. You'll also find links to blog posts, other videos, and other content related to AWS Step Functions and serverless on AWS. I'd like to thank you for making time to join us today. I hope this has helped illuminate step functions and helped you understand a little more about how the workflows are processed, and I hope you've learned something. My contact information is here on the slide if you have any additional questions. Please complete the survey, let us know how we can improve, and otherwise, I'd love to know more about what you built. Thank you.